Good morning, everyone. This is what we hope to be the first of a number of technology transfer showcases sponsored by the National Road Research Alliance. We certainly welcome all of our partners this morning. One of the benefits of being a member of this organization. Today, we're going to be talking about measuring the movement of transportation structures using digital image correlation equipment. And this is something that today I'm going to give you kind of a brief introduction on how we've adopted it here at the Minnesota Department of Transportation. And then we'll more in detailed presentation following that for applications other than pavements. So again, my name is Tom Burnham. I'm a Senior Road Research Engineer with the Minnesota Department of Transportation. And I'll be joined today by DiRienzo, with a staff engineer with RESPEC, and that's the U.S. distributor of the equipment that we've been using. I'm going to switch over to the other presentation. So it'll be about a 45-minute showcase this morning. And I'm going to start just with a 5-minute introduction of how MnDOT has used this particular equipment. The history is we acquired this equipment back in July of 2015, and it consists, and our system consists of a 4-camera digital image correlation system. It's essentially a very high-resolution video camera system that is designed to capture and quantify the movement of things that it's pointed at. And Amy will give a much more detailed description of how this system works. I just wanted this morning kind of showcase how we've adopted it here at MnDOT. Doing a literature search, we kind of identified that we're one of the few, if first, users of this type of system to use it for measuring pavements. It's typically been used for other things in the laboratory or, again, other structures that will be described later in this presentation. We primarily purchased it to replace what we call the rocking beam, and I'll show you a picture of what that is. Being a first adopter, of course, always has its issues, and we had quite a learning curve getting this system up and running, primarily because we seem to be pushing the limits of the system, and that's something that we're very well known for at MnRoad here. Is we're always pushing the limits of trying to find new ways to apply this technology. Well, that was quite a large learning curve, but we're essentially very comfortable with the system now. We're also able to use this for calibrating MnRoad sensors, so that's another application that we found is very useful for this particular system. So again, my business is trying to characterize what's going on with concrete overlays. You can see by this picture here, some panels have been moving around. We're very interested in characterizing how they're moving when a vehicle's traveling over them. And, you know, we can use strain sensors and LVDTs and that type of thing, but really we want to fundamentally know what's happening when a vehicle's traveling over these particular pavements. So these are kind of the movements that we're interested in measuring, you know, whether it's bending of the panel or if it's tipping or you're getting transfer across the joints of the pavement. So this is the infamous rocking beam that I have to credit Steve Olson for being a large part of developing. It essentially consists of a very long piece of metal with LVDTs hanging from the bottom, and the point is that as the truck goes by and the panels move around, this is, you know, a system to measure it with fairly high accuracy and very good precision. As you can see, it's very clumsy, very hard to set up, not very portable, and it has limitations that you have to kind of hang it off the side because you got to get the vehicle through. So again, here this shows at the MnRoad test facility, the MnRoad truck going by, and we're measuring the response of those slabs as the truck goes by. So again, you're limited to measuring what's going on at the edge. That's not ideal. So we found this digital image correlation system. I thought this is a great, you know, way to get rid of all that hardware. And essentially, this system, as it will be described later, you can just point it at things, and it's going to measure how things are moving. So you can see here, We actually took this out on several county roads to measure the movement of, under live traffic. We have a number of targets that we just glued down, and by pointing at those targets, we can measure and do the same measurement that we had with that rocking beam. This system is produced by the iMetrum, called Video Gauge. Again, we're not endorsing any products as far as the NRA is involved, but it has been a useful system that we've adopted. One of the benefits, of course, is that we can start putting things.
You hear the term, but do you know what it means?
Within the lane.
An invasive species is the one that isn't native and whose introduction causes harm.
Excuse me, could somebody mute their telephone line? We're getting some feedback.
Human health. You've probably heard of some of them. Asian carp.
Yeah, got him.
Okay, thank you. So again, as I was saying, one of the benefits of this system is that if you can place a target that doesn't get run over, again, we're doing this at MnDOT under very controlled conditions. Anywhere you can see between the wheels or axles, when the truck goes by, it gives the ability to actually start doing some two-dimensional measurements or measurements within the slabs. Very useful. One of the key elements, you see these plastic triangles laying here. It's one of the things that's required for the system is some measure of a scale. So we know how high that scale is, and that's how it's used for correlation of the data that comes from the camera. This is just a representation of some data. As the truck is going by, you're getting deflection. As you can see, very, very fine precision, down to tenths of a millimeter. So very, very small measurements that we're measuring, and this system has the capability of doing that. And at one point, we actually even pointed the cameras right at the tips of the LVDT to verify that they were both moving in unison. So we're very comfortable that this system has the capability of measuring what we need it to do. This is just a sample of some data from measurements that were done, again, out on the county road system. As the truck is traveling by, this told us that as the axle lands on the panel, it's deflecting down in the beginning. It's not doing an overall rocking motion, as you can see by the far end. Target 8 here is not moving at all. So essentially, we learned that as the wheel hits the panel, it's deflecting down. It's not tipping the entire panel. So these are important things that we're trying to figure out as we're doing our research. As I mentioned before, we also discovered it's a useful tool to calibrate strain gauges. Again, in this case, it was asphalt strain transducers that were being installed at the MnDOT test facility. So again, here you can see we have a test stand, and we just insert the transducer in there, and then we manually pull and compress it. Lighting is a very key concept in this process. You need to have very good light. But one of the things about this video gauge is that it actually is designated as an ASTM extensometer, so that's exactly what you need for doing this type of calibration. We're trying to compare, as you pull the sensor, what the video gauge measures compared with what the system is producing. We learned a lot of things about where to point it. We had some errors in where you're targeting your image, so you can very specifically target certain areas of the gauge. We had to end up going here at the end of the leg. So here this shows, again, the results from the comparison of what the data acquisition system was putting out versus what was actually being measured. And that relationship is called the gauge factor, and that's really what we're interested in calibrating or checking the calibration of these sensors. So with that, hopefully that was kind of an introduction of how MnDOT's been using this particular system, and really now the presentation is going to focus on the other applications that have been the system is being used for, and that's where Amy is going to talk about that. So I'm going to turn it over to Amy at this point.
Okay,
thanks,
Amy,
Tom.
I'm going to give the presentation over to you now.
If you have questions, hit the little raise hand button, and we can probably address them as we go, otherwise we can take questions at the end.
Okay.
Okay, we've got you up.
All right. So just a little more about who I am. I am a licensed professional engineer registered in the state of South Dakota. I have my bachelor's and master's degree in mechanical engineering from the University of Wyoming, and I am a staff engineer for RESPEC. RESPEC is a engineering consulting company. We're headquartered in Rapid City, South Dakota, and we are Metron's U.S. and Canadian distributor for video gauge. And I've been with RESPEC for 4 years, and 4 years ago is when we partnered with Metron. So I've been with us for our entire video monitoring experience. And I specialize in structural video monitoring, specifically developing video gauge for mining applications. A lot of our consulting clients are in the mining industry. And so I've worked extensively with the system for the last 4 years. And the system is called Video Gauge, and it is a digital image correlation package. There's a lot of other softwares out there on the market that do similar things. But in Video Gauge, the correlation is just between windows of pixels. And so the user defines a window of pixels in the image that they want to track. And then the software searches for and tracks the position of these targets from frame to frame. And so down here in the image, can you see my cursor pointing at the screen?
Yes.
Okay, great. The target that we've defined is this red window. And the position of that target at time N is M. And in the next frame, the position of that target has moved from M to M prime, and the software calculates the difference in position, and that would be the displacement measurement, or D. And so it's a really simple concept, except for the software is able to track these displacements to a sub-pixel resolution. And so we're able to make measurements to 1/100th of a pixel. And that is defines the resolution of our measurements. And so if the image is a field scale, something of a bridge or a large section of road, we get 1/100th of a pixel. So whatever area of that structure is projected on 1 pixel, we get 1/100th of that in resolution. And so typical resolutions for structural monitoring is a sub-millimeter, whereas in the lab where you have a much smaller field of view, it's still 1/100th of a pixel, but you're looking at a much smaller section, and so we're able to get micron level measurements in the laboratory using this technology. And so the pattern of the targets is defined by the grayscale of each pixel. And so anything with an adequate pattern can be used as a target. Sometimes we are able to use natural patterns. Sometimes we need to set out artificial targets that have enough pattern that the software is able to identify and track. In addition to resolving the displacement, the software can also calculate strains and rotations between those, the target positions. And so the equipment is pretty simple. The cameras run off of a system controller, which is just a specialized computer. The cameras are all CCD cameras, and so none of the cameras that we use have storage on the camera. All of the data is transferred directly back to the camera controller while the video is recording. And so most of the cameras are powered over the Ethernet cable that also transfers the data, but some of them do need an external power or battery pack, and those are our high-speed cameras that require the extra power. The cameras are mounted just on a surveying tripod, and that's the entire system. And so the controller can be either powered from a main supply or powered off of batteries when you're in the field. Each controller can run up to 4 cameras. Sometimes additional cabling is necessary to synchronize the cameras if you're using a multi-camera system or for high-speed applications. And overall, the system's extremely versatile. And so the speeds are defined by the camera, and then the field of view is defined by the camera lens. And so you spec the camera and the lens to your applications. And so the software is loaded onto the camera controller, and these videos are collected within the software. And the processing can either be done in real time when the video is being collected, or the video can be saved and the measurements can be post-processed. So targets can be added or moved after the fact. And that is required. Post-processing is required for high-speed applications, but for most structural applications, we're able to make real-time measurements in the field. And so the first case study I want to present is of a steel bridge in Somerset, UK. The developers of the software, Metrum, they are based in Bristol, UK. And so some of these case studies that I'm going to present today were collected by Metrum, and then some of them are RESPEC projects. This first one is obviously a Metrum project since it's in the UK. It is a short span rail bridge on this, and the train that goes over the bridge is a rock quarry train. So it's a heavy vehicle, and it's traveling at 90 miles per hour. There's a drive unit on both sides of the trains, and there's 8 cars in between, and we'll be able to pick out in the bridge response each axle for both drive units and the cars. So in this study, we have both video gauge measurements and measurements from potentiometers to verify the video measurement. The video collection rate is 500 hertz because we expect small, short-lived displacements on this bridge. And our video measurement resolution is 1/10 of a millimeter. And so here is the comparison of the displacement results between the potentiometer and video gauge at 1 point on the bridge. As you can see, there's excellent correlation between the two measurements. At the beginning of a test, we always want a static period to define the zero location of our measurement. And as the drive unit passes over that point on the bridge, we get our greatest deflection, which is approximately 1.35 millimeters. And then we see a rebound between the front axle and the rear axle on the drive unit. And then this next peak is the first axle on our first car. So then we have a rebound between the wheels on our first car, the coupler between the first and second car, and then our subsequent 7 more cars. And then we have another great response from our rear drive unit. And so the advantages of using video monitoring for this application over the conventional instrument or that potentiometer is video gauge is fast and easy to set up. Our workers and equipment are out of the traffic, whereas with potentiometers, you have to be able to access the structure, you have to set up your instruments, you have to block off traffic. And so it's a lot more complicated of a setup than just showing up on the side of the road, setting up your camera, and taking a video. We also have the option for post-processing with digital image correlation equipment. We can add measurements after the fact. We can move measurements. So if we miss the peak deflection on the structure, we're able to capture it after the fact, whereas with conventional instrumentation, you set it up at your 1 point, and that's what you got. You have no chance to repeat it without setting up an entire new test. And all digital image correlation packages are multi-point, and so you can set up as many points as you want in the field of view as long as you have sufficient pattern. The next case study that I'll go over is another steel bridge in Ludlow, UK. It is a bolted steel bridge, and this is also a rail bridge for passenger trains that drive at 50 miles per hour and coal trains that drive at 20 miles per hour. And this study is a duplicate study, and so the client brought a Metron back out to take additional measurements of the bridge, specifically focusing on each joint in this steel bridge. And so the bridge is 4 spans. We're focused on one of the center spans over the river. And so since the objective was to focus on these individual joints, 4 different cameras were used. 3 cameras were focused in on each of the bolted joints, and then we have 1 wide view. And all of the videos were captured from 45 meters, or about 150 feet away from the bridge. And so here is our rail bridge, and running parallel to the rail bridge, we have a highway bridge. And so the videos were captured from the highway bridge looking over to the rail bridge. And for this study, the cameras were ran at 40 hertz, and we also expected 1/10 of a millimeter of resolution. And so here are the camera views that were captured from that 150 feet away. And so all 4 of these images were captured using the same model of camera, just outfitted with a different lens. And so these top images of the bolted joints, those will be of a longer focal length lens, whereas a wider angle lens is used to capture the full bridge. And so measurements were made on each of the joints to measure any extension of the joint, so opening and closing, as well as at every stringer there was a vertical displacement measurement set up. And so here are the vertical deflection measurements of the stringer at the mid-joint. Our maximum deflection is 14 millimeters, and so that's quite a bit more than our last bridge, or especially what we would expect out of pavement. And so that's why in this application, 40 hertz is adequate to give us this nice deflection measurement, because we have large deflections and a pretty slow response. And these results are for a coal train, so moving at 20 miles per hour, so also slow traffic. So underneath this green box is one of the bolted joints. And so this green box is what we call a strain map. And so this is available in all digital image correlation packages, and it is tracking every pixel and is making a contour map of the displacements or strains. And so over here we'll have a plot measuring the extension at the top of the joint, and then we'll be able to see a contour map of the strain as the train moves over the bridge. So I'll go ahead and start the video. Up here, so this is just a screenshot out of the software. Up here we have a display of all of our measurement points, and then any graph that we've defined, and then our video image. And so I'm going to pause it right here. And so as the train moves over the bridge, it's deflecting. And this particular joint is open at rest. And so as the bridge deflects, the joint closes. And that's how we, that's you can see that up here in the purple section of our strain map is the compressional strain of the joint closing as the bridge deflects. And then this red section would be the positive or tensile strain, and that is because as the joint closes, that top bolt on the joint is loose, and it's moving away. The bolt head is moving away from the flange, and so we can see the extension there as the joint closes. And over here, there's the extension of the joint. So every time the one of the axles of the train goes over the bridge, we have negative extension or closure of that bolted joint. And so it's, this case study just shows how tailorable this type of technology is. We can use it to really make in-depth investigations of structures and get a complete understanding, as well as quick, simple measurements of the entire bridge, all with the same system. This particular finding of these joints being open, it wouldn't have been possible with conventional instrumentation. So it's something that digital image correlation really offers over conventional instrumentation. And because this is a steel bridge, you can see there's a lot of rust and natural pattern on the bridge itself, and so no access was necessary. We didn't have to put any artificial targets up. All of these measurements were made just using the natural pattern of the structure. And so the maximum extension of that joint was 1.7 millimeters. And these vertical deflection measurements were made, there were 21 stringers, so 21 different vertical measurements were made, as well as these in-depth investigations of all the joints. And so this next case study is of a railway, and it's the example of a high-speed application. So the trains on this rail, the speed limit is 120 miles an hour, but there is rail restrictions in the UK, and if the rail is deflecting too much, then they need to put a speed restriction on the track. And so video gauge was chosen for this study because there was limited access to the track. And so it was impossible to use conventional instrumentation because there was no access. We did need to spray paint targets on the side of the track. And so we needed to get close, but couldn't be close during train traffic. Natural pattern was used to make measurements of the ties and of the ballast, but for the rail itself, like I said, we needed some additional pattern, and so we used spray paint, and that the videos were captured from 7 meters away, so about 25 feet away from the track. These videos were captured at 100 hertz or 100 frames per second, and we have a smaller field of view in this application. We're focused on a pretty short section of track, and so the resolution in this measurement is 0.01 millimeters, or 1/100th of a millimeter. And so as I start the video and you see the displacement response come across, this little bit of vibration is caused by a train passing on the adjacent track, so not the track that we're focused on. And any minute now, our train should be coming along. So I'll pause it and describe what's happening. So here, we have a target on our ballast material, but in the center of our track, we have these spray paint marks that we're tracking the displacement of the rail with. We have a target on the tie clip, and then also a target in our ballast material closest to the camera. And so as from top to bottom, this graph is for our rail deflection, the second graph is for our tie, and then these bottom two graphs, the top one is the far ballast, and then the bottom one is our close ballast. And so the rail displacement, the maximum displacement is approximately 7 millimeters, and then we do see 5 millimeters of rebound for a total of 12 millimeters of displacement. Our tie is displacing more than that. It displaces 9 millimeters down with a 5.5 millimeter rebound. So the most interesting part of this study is the far ballast measurement, because as our train passes, that target is blocked. But every time we have a clear shot of the ballast in between wheels, the software is able to reacquire that target and continue to make displacement measurements. And so we are able to measure the rebound of the far ballast and then the full response of the close ballast material, which is about 7 millimeters down and 2 millimeters of rebound. And so these results did prompt a speed restriction on this rail. A total of 12 millimeters of movement is too much. And similar studies are used to determine the timing and evaluate the effect of ballast tamping. And so it's a quick and easy way to make measurements to schedule maintenance and verify that the vibration has been reduced. So this next case study is a RESPEC case study, and the objective is to evaluate the roadbed support. And so this section of road is on a loading dock, and so it's pier supported, and there was concerns about erosion or damage to the pier. And so we set up targets on both sides of an expansion joint. On both sections of the joint, the road is just supported by the pier. On one side is where they were concerned about damage, and on the other side, the pier is expected to be intact. And so the roadbed was loaded by this mining loader, and we just drove it back and forth across the road. We didn't need to use artificial targets in this application. So the section that we're monitoring is about 20 feet long, and so we needed 8-inch artificial targets, and these 8-inch targets are mounted to steel blocks. And so we expect that they'll deflect as the road deflects, and we'll be able to interpret the road deflection from the artificial targets. In addition to having the targets down the road, we also have them across the path of travel to make sure that the deflection of the road isn't greater on the water side of the road. We are collecting these tests at 10 hertz. This loader is driving at 2 miles per hour maximum, and expect 1/1000th of an inch of measurement resolution. And we did record multiple passes and were able to duplicate the results exactly. And so the loader will be traveling from, I think, from right to left, if I remember correctly. I remembered incorrectly. The loader is traveling from left to right. And so this first graph is for the back far left target, and so the target closest to the water. And then these next four are for our center targets moving from left to right. And so this is our far left target, and this is our far right target. And as you can see, the displacement on the right side of the target is much greater than on the left side. And if you notice up here, I have quite a few zeros, so I have more targets defined in this video that I'm not tracking. And so I've defined targets and then I've turned off the tracking to save computing power. And so here is the responses overlaid. And so the purple line is the far left target, the red line is the left target, the blue line is the right target, and the green line is the far right target. And so you can see the progression of the loader travel based off of when the maximum peak is. And so the far left target responds first and the far right target responds last. And that the displacement is nearly double on the right-hand side, where we were concerned about damage to those buried piles on the pier. And so this did prompt further investigation and rehabilitation of their loading dock. And that the deflection was comparable between the back and the center targets, even though, oh, I thought I had a graph of it. Even though, once again, just like in our railway case study, it was blocked for just a minute. And so for applications like this, you can use flat targets to make measurements. In this case, we didn't have enough pattern on our pavement to make an adequate measurement, and so using out-of-plane targets gave us a better result, but it is possible to use a flat target to make an out-of-plane measurement. And the last case study that I want to go over today is of a parking garage. And so these measurements were prompted by complaints of excessive movement in the parking garage. This field monitoring was completed in less than 30 minutes, and I can vouch for that. I only put 1/4 in the parking meter when I was making these measurements, and I was done before my time expired. And so it was a quick and easy measurement. The distances, so in that 30 minutes, all I did was measure the distances for the plane calibrations. Like Tom mentioned earlier, all of the measurements are calibrated by knowing known distances within your image. We took 4 passes up and down the parking ramp and measured the deflection in real time, just in pixels, and I went back to my office and post-processed all these results. And so this test was also collected at 20 hertz, and we expected 5/1000ths of an inch in measurement resolution. And so here is the response. So we attempted to make measurements on every single beam that we can see in view. I have the beams numbered. The one closest to the camera is beam 1 to all the way to 17. And the beams are twin T molded beams. And so there is each beam is connected to the beam behind it And that's important to remember when we look at the results. And so for these results, the vehicle is driving up the ramp. And so since beam 1 is closest to the camera, it's going to hit beam 2 first. So we'll look at those results first. And we can see the displacement of that front axle displaces approximately 0.08 of an inch. And then we see the response of our rear axle. And when we come over to the beam number 1, we also see the front and the rear axle's response, but the displacement histories look a little bit different between the first beam and the second beam. And that is because beam number 1 is preloaded because of the twin T molding. And so we don't see a clear 2 peaks like we do in beam number 2. And so here is all of the 17 beams. You can see that most of them produce comparable results, but we have a couple beams that show much higher deflection. And that is because when you're looking at the beams in this image, once you get to those far beams, we have very little area to use as our target. And so the software requires at least a 40 by 40 pixel target. And so it's something to consider when you're making measurements. And so we were still able to make measurements, but as we got further away from the camera, the quality of those measurements had more, there was more error in them. And so as you can see, here is just a depiction of as you get further away, our results are diverging from 0.08 inches of deflection, and that is because of the poor quality of target. And so it's not a foolproof system, and care needs to be taken when making measurements and interpreting your results. So in summary, video gauge is a non-contact displacement measurement tool that has been used extensively in the laboratory and has great potential for structural monitoring and is adaptable to lots of transportation applications, especially highway structures. It is a multi-port system, so the user can define as many measurement points as necessary in the measurement frame. They can be done in real time or post-processed. And every case study that I presented today is a two-dimensional case study, but 3D measurements are possible by using 2 synchronized cameras. And so it is a more complicated setup. It takes a lot longer than just jamming in your tripod legs and flipping on your camera. But it is possible to make 3D measurements. It's highly versatile. The exact same system was used for all of these case studies. Just specific cameras and lenses were selected to meet the resolution, speed, and distance requirements. The advantages of digital image correlation technology over conventional instrumentation is no access is needed unless you need to apply artificial targets, and we've gotten pretty creative in how to apply artificial targets when you can't exactly reach your structure. We often use paint rollers on a long stick to roll on sticker targets to our structures. It's relatively fast and simple to set up. There's not a whole lot of equipment, and everything is always a safe distance away from traffic, and that's most important. Safety as well as convenience. No lanes need to be closed. Traffic doesn't need to be diverted to make measurements. And the option of post-process is my favorite because I can go back to my office and do most of the work instead of sitting out in the cold and rain. And not only is it convenient, but I can add measurements, I can move measurements, and that's just not possible with conventional instrumentation. There is some measurement considerations in addition to what I was pointing out during the parking garage case study, just knowing how to use the software correctly. The system, well, the technology is weather sensitive, and so as I mentioned when talking about how the software tracks, the patterns are defined by the grayscale of the pixels, and so any change in lighting will can create artificial movement. The same with heat haze, the same with rain. If your target gets stuck onto something that's moving that's not what you're focused on, there can be issues. The Metrum has built in quite a few checks and improvements for changing lighting and things like that in their software, but it's something that needs to be considered and avoided if possible. Camera stabilization is also an issue, and so if your tripod's sinking or moving in the wind, it's going to affect your measurements. Any camera movement is going to look like structure movement. And so there is ways to subtract out your camera movement by making relative measurements using virtual LVDTs or things like that in the software, but it's an important consideration. And long-term monitoring is a challenge. And so I've been working on long-term monitoring in mines, but we do not have any changing lighting issues. And so outdoor long-term monitoring is just, the digital image correlation is not well suited for those types of applications. Do we have any questions? Before we open up to questions, I want to just quickly thank Minnesota Department of Transportation, especially Tom and Steve, for giving me the opportunity to present today and organizing the webinar.
Okay, go ahead. We'll take a question here.
Bruce Cancos from MnDOT. In addition to pixel displacement, can you also record the direction of the pixel movement?
Yes, and so when you define your planes, you define what direction you want to make measurements in, and so you do not have to be square on. It doesn't just have to be orthogonal X and Y. You can define whatever measurement in whatever direction you want. And so, yes, that's absolutely possible.
Yeah, perhaps Steve can describe, we've made some attempts to measure movement of a bridge, highway bridge, and the fact that you have to set up at an angle. This software has the ability of, you position a plane to enable you to, even though you're at a...
Right, so skewed perspective is something that we've been working on, and we're getting a better handle on that. So we're looking at more bridge structures underneath. The one we're working on has a lot of disadvantages with moving water underneath and reflection of water and light sources, but we're getting better at it. We hope to improve as we go. And we actually, last month, we had Amy come out and to the site and kind of instruct us on what we're doing correct and not so correct.
I just have one comment that most of our case studies were, again, slower kind of speed on the camera. Just for comparison, we were actually trying to push the camera to 1,000 hertz. So again, trying to capture high speed, what we envisioned high speed necessary for the very minute measurements we were trying to make on pavement. We felt it necessary that we were up at 800 to 1,000 hertz. That was pushing the system. So again, they've made some improvements to the system, and we are now able to capture something at that very high speed resolution.
So the faster your movement and the smaller your increment of movement is, a higher speed is necessary. So maybe did say that with large movement, we can cut the sampling frequency down a lot. Most of our pavement movement is in the tens of thousands or hundreds of millimeter movement, so a lot more sampling, a lot more data, a lot more space. We're talking gigabytes of memory.
Any other questions?
I don't see any online.
Okay, thank you for attending the showcase. Hopefully you've learned some of that and other applications for this technology. Hope to see you again.
Thanks, Amy.
Thank you.